To show the difference here, I'd like you to now draw the 100 plane in a Cartesian coordinate system. So here you're going to draw the Cartesian coordinate system and a cube, and then draw the 100 plane. Okay, so practice your sketch work here and resume the video once you've got a plane for the 100. Okay, so hopefully you settled on steps like this. So working our way backwards, our Miller indices was of course 100 rounded parentheses. There's no need for a reduction, so we can't predict the outcome at step 3. And we simply sort of spread those Miller indices values out at 100. Those help us know where we are going to intersect the planes in our Cartesian coordinate system. So along the x direction, I know we intercept here at this one equivalent unit of A. We never intercept the y, so I cannot put anything along this axis. So I'm parallel to that. So plane of interest lies somewhere here, and it may tilt forward or back depending on the final bit of information. Okay, so let's just eliminate those ideas to help give us a nice clean diagram here. Okay, and then we ask the question, where does it intercept the z-axis? Well, it never does either. So the only way to have a plane here that does both of those is to consider a plane here that is parallel to the z direction and the y direction. Okay, so something like that. That's obviously larger than we need. So if we were to show that more simply in our diagram, we are now considering the 100 as this plane here. So it is one of the faces of our unit cell. Okay, so there you see this answer, 100, is a face of the unit cell, and previously the 200 was halfway along. And hopefully you can see that we are now talking about different planes here. So the act of reducing does have an impact, provided there's differences within the unit cell. Body center cubic versus simple cubic emphasizes that. Okay, good. So that other diagram's here for reference as well. Okay, here's another example to make sure you can do this one. So here you can see that we've got a plane on angle through a lot of angles on our unit cell. So we should get some interesting coordinates here. I think it's fair to assume that here we're intersecting at one whole unit of B, halfway along of A, and here three quarters of the way along the C direction. Okay, so pause the video once you've had an answer. Okay, so hopefully you settled on identifying the places where we intercept, so that's our important part. So we were a half unit along in A, one whole unit along on the Y direction, so one whole B unit there, and like we said, 3/4 of the way up for our final intersection point here. The next process was to execute a reciprocal. We saw how that takes care of infinity signs should we have a plane parallel to the axes. So we still do that here. So our reciprocal now is going to be ultimately 2, 1, and 4/3 now. So we still have a fraction here, so we need to do a simplification to try to get to whole numbers. Again, we never have fractions in our Miller indices for planes. Okay, so we definitely do a simplification here. Okay, so in order to do that, we need to multiply by 3. So our after reduction, we end up with 6, 3, and 4 as the information reflected for that plane. And then, of course, we finish that off with parentheses. So this plane shown here is the 6, 3, 4 plane. Very good. Okay, and so like we saw before, we had family of directions. We can have family of planes. So in our similar ideas here, all the planes that are crystallographically equivalent, that is to say that they have similar atomic packing, how they bisect atoms throughout the lattice of the crystal. If another parallel plane has the same atomic packing, we can consider it as being part of that family of planes. So in a cubic crystal, the family represented by the curvy parentheses here, 1, 0, 0, has all these planes above that are parallel and equivalent. They have the same atomic packing if we consider the extended models. Okay, now we haven't addressed hexagonally close packed systems. Here the ideas are very similar in that we need a fourth bit of information. So here we're kind of pushing ourselves outside of our comfort zone in that we have to move out and away from our Cartesian coordinate system and now use a 4-axis system to represent space. So we'll put one of our dimensions along the z as normal, and we're going to position the rest of the cell and then at the origin of this new set of axes that has 3 axes in the plane and 1 vertical. Okay, so in this case, for a plane in a hexagonal system, the ideas are therefore going to be the same. Okay, so where do we intercept these planes? Do some of them never intercept? And if so, we'll reflect that with infinity signs. So this blue plane here, you can see here that it intersects at exactly 1 unit of A. It never intersects the A2 axis, so we'll give that an infinity sign. And then it intersects the A3 at a -1, so we would have to access the negative space here for that intersection point of that plane. Okay, so -1 value there. And then the whole unit cell is C tall, so we finally have the plane intersect up here on that Z axis with 1 value there. So you can see here as we go through the same procedure, reciprocal, reduce, and use parentheses, that we now have a 4-digit Miller-Brabé indices for this plane, which represents the information of a hexagonal system. So seeing information with 4 digits helps you recognize a hexagonal system. Okay, so an idea that we can build off this now is the planar density of atoms. So this is the equivalent idea that we had for a vector or a line and how many atoms lie on that line. We can do this now for a plane. So here the idea is going to be, let's consider the number of atoms centered on a plane. And again, the key idea there is that the atom center must lie on that plane, not a portion of the atom, not the top hemisphere of it just being cut off by the plane, but the center of it must be on that plane if we're going to count it. And then we need to determine the area of the plane this time, not the length, but the area of it, okay? So similar logic there. In planar density, this teaches us something about how much atoms density do we have in a certain unit of area, and that's going to reflect things like porosity, strength, corrosion resistance. The more atoms present, the more robust the material could be. Okay, so here's an example where we've got iron foil that can actually be used as a catalyst in things like catalytic converters, or the generation of ammonia for fertilizer applies iron. And at some certain temperature, we know that iron can accommodate a BCC lattice. And so we can start asking directions. So here we might be asked to draw the 100 crystallographic plane for iron. And ultimately, let's populate our diagram with some atoms to make sure we can reflect the body-centered packing of atoms in this diagram. Okay, so take a minute to put a sketch for your direction, and then ultimately put some atoms into this drawing. Resume when you're ready. Okay, so the 100 plane, we're going to intersect at this one value here. Okay, so I know I've got one value listed there for my intersection points. A 0, as we saw, reflected an infinity value via our reciprocal. So we will never cross the y, which is reflected here. So if you're getting good at these, you can skip the tabular approach and just kind of try it. I urge you to be cautious, though, and practice a few times before you just go for it. So we never intercept the y, and we never intersect the z. And so, of course, we're talking about this plane here again. That's the only plane that can cross at one unit along the x direction and never cross the y and the z. And we know that this is a body-centered cubic. So in this system, to populate atoms that are present on this plane, I know that there's atoms at the corners. And of course, there's one behind in the middle, giving us the body-centered feature. And I'm going to kind of leave it there. So a body-centered cubic plane has a quarter of an atom disk present. Okay, so notice I'm considering here the plane. It's no longer an eighth as we count it, but we've got a quarter of that circle because we're considering the planar information. Quarter. Okay. Okay. So here's sort of some other diagrams that help us. We saw that 100 represented the front face here of that cell. Of course, behind it is that plane, and we have a quarter of a circle that represents the cross-section of an atom. Okay. So a follow-up question might be to say, what is the planar density for this plane, provided that we know the radius now? Okay. So here's how we can look at that. So we've seen before, and I will just sort of skip that part, but we've done calculations to help us use radius information to ultimately understand the dimension A here. Okay, so we know through Pythagoras analysis, things like that is reflected here, and that drawing there, where the packed direction where spheres are touching along that hypotenuse, that we can determine the length of A here. Okay, so in short, we know that the length of A here is 4 divided by root 3 times the radius information of the atom in question. Okay, and then if we were considering that 100 plane, which was that face there, we said that we are counting this portion of an atom as a quarter of the disk that is the whole circle of the atom. So 4 features there gives us 4 atoms in this plane. So 4 times a quarter gives us this value here. Okay, so that's our numerator 1. We need to divide through by the area. So of course the area is A squared, which is going to be this value squared. And after running that math, you can see that here we're going to have an answer here of 12.2 atoms per square nanometer. Okay, again, hopefully that means something to you. That's now telling us how many atoms lie in this plane across the material. So 12.2. Values that are very high might represent a higher density of atoms to push through or to corrode through. Values that are low might be more porous, and very small molecules like hydrogen gas might seep through that direction preferentially, as an example, as is the case with hydrogen storage for fuel cells and other kind of gas storage problems in engineering for aerospace, as an example. Okay, and as a follow-up, I ask you to consider here the option for the 111 this time for the body center cubic iron using the same information we had, and see if you can do this planar density as an example. This one is a bit harder. We'll give you a bit of a pointer here. Here's the cubic lattice. We have numerous cells built up here. We know that the body-centered atom is in the center of this sphere, and you might be considering at first glance that this 111 plane, shown in the sort of pink here, you might be wondering if it cuts this body-centered atom in half. And so to help you with that, the answer is no, it doesn't, because it's right at the middle. The only way that could happen is if this plane actually intercepted along that direction there. Okay, so that plane would need to cut our cube in half perfectly along here in order for us to get that body-centered atom located with its center right on the plane. So this spot here, the center of that central atom, does not lie in the plane of interest, in this case the 111. And to imagine that, you can take this red plane that I've tried to do and imagine tilting it forward until we end up with the purple plane in question. Okay, so that's a bit of a hint to help you with that before I let you loose, and let me just clean that up so you've got that information for you. So attempt to calculate the planar density here, given the information that you've already had. Okay, once you've had a chance, maybe resume the video and we'll walk through the steps together. Okay, so planar density, of course, number of atoms in the area of the plane. So numerous ways to kind of tackle this. Just for offering a different approach here, we've got an answer here where we're going to determine the area of this parallelogram. You could also determine the area of the triangle if you wanted. The idea here is that the numerator, the number of atoms in the plane, we are not going to get something from that body-centered atom. So you see that reflected here, that atoms below and above the plane of interest will not count. Okay, so really it's the blue atoms only that we are going to count. So in the purple triangle here, we have a sixth of an atom, a sixth of a disk of an atom at each corner, and so 3 times the 6 would give us a half an atom of count in that triangle. Because 2 red triangles add up, 2 of those purple triangles add up to my parallelogram, you can imagine that we're going to have a numerator here that's twice as big. So 1 whole atom there. Through similar kind of analysis of the dimensions, we saw that the diameter here, the hypotenuse here is root 2a, and so that's information we can use to help us with calculating the height of either the triangle or, in the bottom case, the parallelogram. So once you run an analysis there to help determine your height, we now have the information to determine the area of the triangle above, if you want that method, or what's on screen here is the area of the parallelogram. So the area of a parallelogram is one of those edges times the height. Okay, so that we see that here. Area is equal to the root 2a for the edge length times the height. We know the height here is root 3 by 2a, so the two root 2's end up canceling, and we end up with simply just the numerator of root 3, and we leave behind, of course, the a. So we end up with root 3a squared. Applying what we had from earlier on what the identity of a was in terms of radius units, we can now install that. So 4 root 3 by 3 times the radius that was offered in the question, and we got to square all that, and then, of course, multiply by root 3, and we get our final answer here. Okay? And so in this case, you'll end up with 7 atoms per nanometer squared. And so here we're going to have a lower value for the number of atoms per unit area. Okay? To give you kind of a better feeling, if you had a meter of this plane exposed, a meter squared exposed, about the area of maybe your desk, we were talking about still a very small number of atoms, not even a mole of atoms exposed on that surface. Okay, so those are some calculations we can do now that we know things about naming directions and planes and points within a unit cell lattice, and that should help you with your homework.